This is Jack Jackson. This is going to be a first of a series of videos about transformations. And this part of geometry ties in nicely, connecting several other things. We're going to connect to courses like college algebra and trigonometry, where we look at some elementary courses where we look at graphs of relations and functions, and we're going to learn how to transform those. We're also, of course, going to look at this very physically, geometrically. And then also, eventually, we'll get to the point to where we can look at these things via matrices. And when we do that, then we tie into courses like linear algebra and abstract algebra, for example. So there are a lot of connections with this last unit with other areas of mathematics. So the first type of translation we want to talk about is a translation. Now, the way this works in Sketchpad, let's do it that way first, is we take a figure here, okay, and I'll just start with a blank page here and just show you. So if we have any figure here, we can make a vector, and basically a vector is a directed line segment. We might use this appearance tool here to give this thing an arrow head at the end. Now, so you'll basically see a vector as a directed line segment, so it has both magnitude and direction. The magnitude is given by the length, that's the magnitude or length or norm of the vector, and then the angle it makes with a horizontal is the direction angle. So it can be given basically with an r and a theta, or a magnitude and a direction angle. It can also be given to it in component forms by saying how much it goes left or right, a delta x component, and then delta y component, how much it goes up or down. But in any event, we can, in Sketchpad, we identify the vector by clicking on the original point and then clicking on the terminal point in that order, and go to transform, mark the vector. Then we can, let's take that and make it, just to use some color here, let's maybe make that purple. And then here's our pre-image points here. We'll make them a bright blue here. And then we take this, let's give them some names. Okay, and we take this thing here, highlight it, and then go transform, translate by the marked vector. We can also specify how far right or left and up or down to go, or at what distance and angle. Or we can do it based on the one that we have here, so we can translate by that. So this is controlled by the vector, so as this point moves from initial point to terminal point, we can see that picture moving in motion, and this set over here is called the image set. And so we typically will label these with a prime on it for the image. So the original point is A, that's called the pre-image point, and its image is A prime. So this is a function which maps points to points in the plane. So in fact, it actually maps every point in the plane to another point in the plane, actually every one to a different point. There are no points which are fixed by this transformation. And but it's also a linear transformation. So what that basically means is if A is mapped to A prime and B is mapped to B prime, then all the points between A and B are mapped between A and prime and B prime in such a way that this is it preserves line segments. Of course, that also preserves lines, and it's going to actually preserve distances as well. So this is in fact what we call an isometry, and that's something that preserves distance. Turns out if it preserves distance because of the side-side-side triangle property, it's also going to preserve angles. Mapping that preserves angles is called conformal. So this is a conformal mapping as well as being a linear transformation, and in fact it's an isometry. So these two figures are exactly the same size and shape, and so that's what we mean by a translation. And you can see how to do it in Sketchpad. So here we can see this one's controlled by this particular vector. We can see this going here, and so what happens is the way you can tell this is a translation is if you connect every point from the pre-image point to the image point, it's the same vector. Now remember, a vector has magnitude and direction, but it doesn't really depend on the position of the vector. So it's the same vector no matter which place I place it, whether I place it here or here. This is going to be pre-image point to image point. That's going to go from pre-image to image and so forth, anywhere on this. And so anywhere you place it doesn't really matter. It's the same vector as long as it's the same length and the same direction, meaning all of these are parallel with the arrows on the correct end, in this case the lower right side, and they all have the same length, so that's the same vector. Now, you can see this point here, as it moves from tail to tip, you can actually see that these all follow the vector as they go from pre-image point to image point. I can even animate that using an animation feature. Now, how could I use some other things? So, for example, if you had transparency paper or something like patty paper, something like that, you could place your paper over this, trace the original pre-image point, FHG with a straight edge, and then on your tracing paper, put a point here at the tail, and carefully, without rotating, slide that point on the tail from tail to tip. So watch out down here on the vector down here, and it just slides from tail to tip. Now while I do that, look what happens up here on the triangle. It actually slides along that vector. And so you can do that sort of as a check with tracing paper. So in Sketchpad we can define that in terms of a vector given by an actual directed line segment here, like I did on the previous one. I can also go here, specify a distance parameter, make a parameter distance, which I can go under number and new parameter and make a parameter for distance, and then one for angle, and then go here and say mark that and say transform, mark the distance there, go to angle, transform, mark the angle, and then when I go down here and select triangle MNO and then say translate, I'm going to select something here. I can do by marked vector, by the new vector that's given by angle distance. Let's go ahead and do that. So distance, transform, mark distance, angle, transform, mark the angle, and now we select this here, and I can say transform, translate in polar by the marked distance and marked angle. Or if I have it in component form, basically a rectangular form by horizontal by marked distance and marked distance for vertical. This is basically a delta x and a delta y. I can do it that way, and this will give me my translated image. Okay, so that's how we can use the command in Sketchpad. Now, how can we construct this in, say if we just had a compass and straight edge. Suppose we were going to do this on our paper. So remember, classical constructions in geometry are done only with a compass and a straight edge. And remember that we're not using any marks on the straight edge. We're not using it as a ruler. No protractor even. Well, let's go over how we could do that. Remember that the key is back here, is that what we want to do is we're given this vector and we're given some pre-image up here. What we want to do is to make copies of the vector, because once we make copies of the vector, the end of the vector determines the image points. So when we say copies of the vector, what do we have? We have something that's the same length and parallel. Well, if we basically connect up the tail to H and the tip to H prime, we've got a little rectangle. We've got a, let's see if I've got it here. I've got it for G anyway. So here, for example, you can see connecting G to the tail and G prime to the tip. So beginning to beginning and end to end. And notice that we actually have a parallelogram here because we know that anytime we have a quadrilateral with a pair of sides that are both opposite and parallel, we've proved that that is actually not only just a quadrilateral but a parallelogram. Now we use one more fact about parallelograms, that parallelograms have both sides of opposite both pairs of opposite sides congruent. In fact, if both pairs of opposite sides are congruent, it has to be the parallelogram that we need. And so that's going to give us a method of constructing it, and here we go. So what you do is first set your compass to the length of the vector. So put your pointy in here and the drawing in here. Now you don't have to make this full circle, you just need to make a little mark right here at the end of it. Now go down here to whichever point we want to move, let's say A, and make a circle centered at A with that same radius without moving it. So we know that A prime has to move that far, so it has to be on there. Furthermore, we know A is kind of up and to the right, so you really don't have to draw the whole circle. We know it's going to end up over here in this part somewhere. So if you want to just maybe draw an arc across here somewhere and leave out this part down here, that would be fine. In fact, it may be advantageous to do it that way, since later on we're going to start, if we make too many marks on here, it's going to get a little messy. So just make part of the arc here, as long as you're sure that it's going to cover, we're kind of going up like this. A prime is going to be right in here somewhere. Make an arc a little longer than you think you need, but just in that part. Now, you don't actually have to draw this in, but this is going to be one side of our parallelogram, and we have the other side. So we set our compass to that length, and we'll make a little mark right here. Okay? And again, you don't have to draw this full circle right here. Just make sure that it actually makes a little bitty mark right here at A. Now, remember the pointy end of your compass is on the origin of your vector, and the writing tip is over here on A, making a little small arc there to make sure it's set the right distance. Now just take your whole compass and slide it. Slide the pointy end down to the end here, and of course this end will slide down here, and now make another mark. So it's start to start, finish to finish. So start here at O and go to the starting point for A. Slide the compass down to the terminal point T, finishing point here, and it's going to mark out the finishing point. A prime has to be on this circle, but also has to be on this circle. Now they actually cross once over here, but that's obviously not the one we want. The one we want is going to be over here. So right there where they cross is going to be A prime. Now if we wanted to finish it up, I don't have it all drawn in here, but if I finish up this point to this point, that would finish up my parallelogram. I have drawn in the vector so you can see it there. But I'm going to use, at least right here, I've used a kind of a light purple for the vector, blue for the pre-image, and this is the image point, so I'm going to put in red. Alright, so that gets us 1 point. Guess what? We redo this. Now luckily, since it's a linear transformation, there are infinitely many points here. Luckily we don't have to do this infinitely many times. We only have to do it for the 3 vertices, and then the straight edge will finish up. So this is what it looks like when you're finished. Now if we also put the construction for B, there we go, same steps. Okay, so let me hide everything else here and just do the construction for B. Okay, so we make sure that whatever distance it is from O to T, that circle is the same size as this one, centered at B. And in fact, if you want, once you measure this from O to T, you can go ahead and make the circles centered at B, A, and C all at once, if you can keep track of it. So we know B prime is on there somewhere. Now, how far out on that? Well, measure start to start and finish to finish. So go from O to B, the length of that line segment. In other words, make this arc here a little bit from O to B. No, not that one. I don't have that circle drawn in here. So it's from here to here, but it'll actually make a little mark, just a teeny tiny mark right here. Take the compass, then slide it, start to start, go finish to finish. So slide it to here, and this is going to be the radius of your circle that you need here. Again, you don't need this full circle. Just do a little mark here to see where it crosses the part of the circle that you drew here. So you might just have just a little portion of a mark right in here, and then a little portion of a mark right here where they cross as B prime. Similarly, there's C prime. Now, if you show all of this, and especially if you start making full circles, you will get a lot of marks on there. Okay? So it can get a little bit messy, but again, you don't have to make these full circles, so it's not quite as, doesn't have to be as messy as it looks here. Plus, you don't have to draw in these sides of the parallelogram. In fact, you don't even really have to draw in the vectors, although it is maybe instructive to see the vectors there. Okay, so some of this is a little bit extra in terms of what was actually drawn. So that's how you can use that. Now, if we have a grid can be very useful in working with translations. So here's what we call a lattice polygon. It's points for the vertices have integer coordinates. Okay, and here we have also a lattice vector. So this vector in component form is right 1, 2, 3, 4, 5 down 2. So this would be 5, negative 2, which we would write this way, right 5 down 2. That's how we would write it in component form. So that's the change in x, or horizontal change, and that's the change in y, or vertical change. So this is up 5 and down 2. Okay? From where? Well, from anywhere. So, for example, I could take point A. Did I say up 5? I think I meant, what did I mean? Right 5. Fix that. Right 5 down 2. So delta x, of course, is left to right. Delta y is up or down. So right 5 down 2. So we're going right 1, 2, 3, 4, 5 down 2. So we could do the same thing for A. Go right 1, 2, 3, 4, 1, 2, 3, 4, 5 down 2 would put me right there. B, right 1, 2, 3, 4, 5 down 2. And then connect those points up because A and B are connected, A prime, B prime are connected. And so forth. And so this is where you end up for an image. And I've drawn in all the vectors. These are more copies of this same vector, which in each case should be right 5 and down 2. So for a grid, it works very nicely. Now let's look what happened to the coordinates here. A was negative 6, 4. Okay. So, let's see. I don't want to do that. Let's just... So A is negative 6, 4. And when we go right 5 and down 2, we get A prime is, what is it, negative 1, 2. Okay, what's the shortcut? Well, notice that if I take the negative 6 plus 5, I do get the negative 1. So that's how we get that. And I take 4 plus the negative 2, and that gives us positive 2, and that's the 1 there. So all you have to do, this is the change in x, so you just have to add that to the x coordinate, and then add whatever that is to the y coordinate, and you got your new point for your corresponding image point. Okay. Now, in our next video, I will look at how this relates to graphing when we're graphing, say, relations or functions like in college algebra or in trigonometry or pre-calculus or calculus, and we want to see how these transformations will play out in terms of formulas, because once we have a coordinate grid, now we can compare formulas, algebraic formulas, or equations relating a set of points, okay, which is essentially gives us a graph, and how we can see how these translations show up in the formula, the table, the graph. Okay, and we'll pick up there on the next video.